In the summer of 1977, two identical spacecraft left Earth within weeks of each other, carrying golden records, plutonium batteries, and a set of instructions so ambitious that no one who built them truly expected either machine to still be working half a century later. Voyager 1 launched second, but flew a faster, tighter trajectory, one that would eventually make it the most distant human-made object in existence. Voyager 2 launched first, on a slower, more patient path, one that would take it years longer to reach the same distances its twin would cover in a fraction of the time. For decades, that difference in speed made Voyager 1 the name everyone remembered. It reached interstellar space first. It became the headline, the milestone, the spacecraft mentioned in classrooms and news broadcasts around the world. But somewhere in the long shadow of its faster twin, Voyager 2 was quietly doing something no spacecraft before it or since has ever managed to do. And the data it sent home did not just add a footnote to the history of space exploration. It rewrote entire chapters of what scientists thought they understood about our solar system, about the giant planets at its outer edge, and about the mysterious boundary where the sun's influence finally gives way to the vast dark of interstellar space. Both spacecraft carried the same golden record, the same suite of cameras and instruments, the same basic design built by the same engineers at the same laboratory. On paper, they were twins in almost every meaningful sense. But the paths chosen for them, decisions made years before launch, based on which targets mattered most and how much time scientists were willing to spend getting there, would end up separating their legacies so completely that most people today can name Voyager 1's crowning achievement without ever having heard what its twin actually accomplished. To understand why Voyager 2 matters so much, you have to go back to the choice that shaped its entire mission before it ever left the ground. Both spacecraft were built to take advantage of a rare planetary alignment, a geometric gift that happens roughly once every 175 years, when Jupiter, Saturn, Uranus, and Neptune line up in a way that allows a single spacecraft to visit all four using a chain of gravity assists, slingshotting from one giant planet to the next without carrying anywhere near enough fuel to make those journeys alone. It was an opportunity so rare that engineers at NASA's Jet Propulsion Laboratory knew missing it would mean waiting well over a century for the next chance. Voyager 1 took the faster, more direct route through the inner leg of that alignment, prioritizing close, detailed flybys of Jupiter and its volcanic moon, Io, and then Saturn and its smog-shrouded moon Titan, two targets mission scientists considered too scientifically important to risk losing. It got spectacular, groundbreaking data from both, but that trajectory came at a permanent cost. Once Voyager 1 used Saturn's gravity to bend its path and get a close look at Titan, it was flung up and out of the flat plane in which all the planets orbit, sent on a course toward the stars that would never again bring it near another planet, ice giant, or major moon. Voyager 2 made a different journey, or rather, its mission planners made a different, quieter bet on its behalf. They kept it on the slower, flatter trajectory that preserved its access to the full outer solar system, sacrificing some of the intimacy of its Saturn flyby in exchange for a shot at worlds no spacecraft had ever approached. It meant Voyager 2 spent far longer traveling between targets, years of relative silence, and routine cruising between each dramatic encounter. It meant the mission's most spectacular chapters were still years, even decades, away when Voyager 1 had already claimed its headlines. But it also meant that after Jupiter and Saturn, Voyager 2 kept going and going until it did something that has never been repeated in the history of space exploration, something that, as of today, still stands as one of the loneliest records in all of planetary science. It became the only spacecraft ever to fly past Uranus. And then, 3.5 years later, after a journey of well over 1 billion additional miles through the emptiest stretches of the solar system, it became the only spacecraft ever to fly past Neptune. To this day, every image humanity possesses of those two ice giants up close, every measurement of their rings, their magnetic fields, their bizarre and lopsided magnetospheres, every discovery of their moons and their strange geology comes from a handful of days in January 1986 and August 1989, when one aging, increasingly weathered spacecraft swept past each of them at tens of thousands of miles an hour and never came back for a second look. Think about what that actually means for how much or how little we truly know about our own solar system. Uranus and Neptune are not obscure, minor worlds sitting on the margins of astronomy textbooks. They belong to an entire category of planet, ice giants, distinct in composition and structure from the gas giants Jupiter and Saturn, and by some estimates, the most common type of planet found throughout the galaxy. More common even than small rocky worlds like Earth or the enormous gas giants that dominate popular imagination. And yet, almost everything we know about this dominant class of planet in our own cosmic backyard comes from a single flyby of each conducted decades ago by a spacecraft that was never designed to linger, never built to orbit, never given more than a few days near either world before its momentum carried it onward into darkness. No orbiter has ever been sent to Uranus. No orbiter has ever been sent to Neptune. No lander has ever touched down on any of their moons. Every textbook diagram, every planetarium show, every scientific paper modeling their interiors, their storms, their magnetic fields, or the chemistry of their atmospheres traces back to Voyager 2's brief, irreplaceable encounter with each. Voyager 1 flew past neither. It could not have, even if mission planners had desperately wanted it to, because its trajectory decisions at Saturn had already locked it permanently onto a path that placed the outer ice giants forever out of reach. At Uranus, Voyager 2 found a planet unlike any other in the solar system, tilted almost completely on its side, spinning like a rolling ball rather than a spinning top. Its axis tipped more than 90 degrees away from the plane of its orbit around the Sun. Nobody fully knows why, even now. The leading theory involves an ancient catastrophic collision, a young Uranus struck by something massive enough to knock the entire planet over and never quite tip back into alignment with its neighbors. Voyager 2's instruments found a magnetic field wildly offset from the planet's physical center, and tilted at a steep, almost sideways angle from its rotation axis, unlike anything seen at any other planet in the solar system, suggesting the magnetic field is not generated the way scientists had expected, not from a simple, symmetrical internal dynamo deep at the planet's core, but from some churning, electrically conductive layer of slush closer to the surface, a layer whose exact composition scientists are still debating. It found new moons circling in that tilted, sideways system. It found a set of thin, dark, previously unknown rings. It measured a magnetosphere so strange, so twisted and asymmetric because of that extreme axial tilt, that it behaves almost like a corkscrew as the planet rotates. And scientists are still building computer models today, trying to fully explain how charged particles move and behave inside something so geometrically bizarre. Then, 3.5 years later, Voyager 2 reached Neptune, and it did something even more remarkable, delivering what many mission scientists still consider the crowning achievement of the entire Voyager program. It became the first and only spacecraft ever to see this farthest major planet up close, a world so distant that sunlight reaching it is roughly 900 times fainter than sunlight reaching Earth. It found the Great Dark Spot, an enormous storm system large enough to swallow the entire planet Earth inside it, churning violently in Neptune's atmosphere, and clocked the fastest winds ever recorded on any planet in the solar system, gusting at speeds exceeding 1,500 miles an hour, fast enough to flatten anything ever built on the surface of our own world. It discovered Neptune's faint, dark partial rings, confirming what ground-based astronomers had only glimpsed as fragmentary, mysterious arcs years earlier without ever being certain what they were looking at. And it made, perhaps, its single most consequential discovery of the entire mission at Neptune's largest moon, Triton, a world so cold and strange that Voyager 2's cameras caught active geysers erupting directly from its frozen surface, nitrogen ice volcanoes venting dark plumes of material miles into a thin, hazy atmosphere, making Triton one of only a handful of places in the entire solar system where active eruptions have ever been directly observed and photographed by a passing spacecraft. Scientists studying Triton's peculiar backward orbit, moving in the opposite direction to Neptune's own rotation, unlike almost every other large moon in the solar system, concluded it was almost certainly a captured world, a former Kuiper Belt object pulled in by Neptune's gravity sometime in the deep past, which meant Voyager 2 had, almost by accident, handed humanity its first close-up look at a body from that distant, icy region of the outer solar system, decades before any mission was ever specifically designed to study one. Getting those Neptune images at all was its own quiet miracle, one that rarely makes it into the highlight reel but deserves to. By the time Voyager 2 approached Neptune in 1989, sunlight at that distance was so faint that the spacecraft's cameras, designed years earlier for the comparatively bright conditions near Jupiter and Saturn, struggled to capture anything without long exposures that would smear every image into a useless blur as the spacecraft raced past at tremendous speed. Engineers back on Earth solved the problem by rewriting Voyager 2's onboard software from a distance of billions of miles, essentially reprogramming a computer far less powerful than a modern pocket calculator to compensate for the spacecraft's motion during each exposure, nudging its orientation in tiny increments to keep the image steady while still gathering enough of the faint, distant sunlight to produce a usable picture. It worked. Some of the most iconic images ever captured of Neptune and Triton exist only because a small team of engineers found a way to solve a problem in real time, across a communication delay of more than 4 hours each way, on hardware that had already been flying for over a decade with no possibility of a repair visit if anything went wrong. None of that alone would be enough to say Voyager 2 rewrote everything scientists thought they knew. Plenty of missions deliver a single spectacular chapter, and then fade quietly into history. What makes Voyager 2 genuinely different, what elevates it from a remarkable planetary tour into something closer to an ongoing scientific revolution, is what happened decades later, long after both spacecraft had left the planets far behind and were creeping, at a snail's pace by cosmic standards toward the true final edge of the sun's influence. Voyager 1 crossed into interstellar space first. In August 2012, a milestone celebrated around the world as the moment a human-made object finally left the bubble of charged particles blown outward by our sun, known as the heliosphere, and entered the space between the stars for the first time in human history. It was a genuine historic triumph, front-page news across the planet. But there was a problem, one that quietly limited exactly how much Voyager 1 could actually tell scientists about that crossing. Years earlier, in 1980, shortly after its own flyby of Saturn, the plasma science instrument aboard Voyager 1 had failed. This was the instrument specifically designed to directly measure the density, temperature, and flow of the charged particles, the plasma that Voyager was moving through at any given moment. Without it, when Voyager 1 finally crossed the Heliopause, the boundary where the outward pressure of the solar wind gives way to the pressure of interstellar space, scientists had to infer what was happening around the spacecraft indirectly, relying on other instruments, on clever mathematical workarounds, and on sudden jumps in cosmic ray readings, rather than measuring the plasma itself directly as the crossing happened. It was a bit like witnessing a historic event through secondhand accounts and circumstantial evidence instead of watching it unfold with a working set of eyes. Useful, groundbreaking even, but fundamentally incomplete. Voyager 2's plasma science instrument never failed. It was still working, still faithfully returning data, when Voyager 2 reached that same fundamental boundary in November 2018, 6 years after its twin, and that single surviving instrument changed everything about what scientists could actually learn from the crossing. For the first time in the history of space exploration, humanity had a direct, working, fully functioning instrument recording exactly what happens to the density, temperature, and flow of plasma as a spacecraft physically moves from the solar wind into true interstellar space. It is the only such direct measurement humanity has ever obtained at this boundary, and it will very likely remain the only one for a long time to come, since no other spacecraft currently traveling toward the edge of the solar system carries a working plasma instrument capable of repeating it. What that instrument found did not simply confirm what scientists had expected going in, it upended it. Researchers had long modeled the heliopause as a relatively simple, sharp boundary, a wall of sorts, where solar wind plasma abruptly stops and denser interstellar plasma just as abruptly begins, almost like crossing a clean line on a map. Well, Voyager 2's direct measurements revealed something far stranger and far more intricate. Instead of a single clean transition, the data showed a much more complex, layered structure. A boundary marked by unexpected gradual changes, turbulence, and pockets where the two environments seemed to bleed into one another rather than meeting along a crisp, well-defined edge. It suggested the heliopause is porous in ways nobody had fully predicted, allowing some interstellar material to leak inward and some solar material to leak outward, blurring what scientists had long imagined as a hard, impermeable boundary separating two entirely separate cosmic environments. Even stranger was what Voyager 2 detected in the region just before it crossed over a turbulent zone scientists call the heliosheath, the compressed outer layer of the heliosphere where the outward flowing solar wind slows dramatically and piles up against the counterpressure of interstellar space pushing back from outside. Voyager 2's instruments recorded unexpected spikes in the density of galactic cosmic rays arriving from far beyond the solar system, alongside sudden corresponding drops in the lower energy particles native to our own solar system, and the precise timing and shape of those changes did not match the predictions built years earlier from Voyager 1's indirect secondhand data. The two spacecraft, crossing the same fundamental boundary in different locations and at different points in the sun's roughly 11-year activity cycle, ended up painting two noticeably different pictures of what that boundary actually looks like at any given moment. That meant the heliopause was not a fixed, static shell at all, the way early, simpler models had imagined it, but a dynamic, almost breathing structure, expanding and contracting, thickening and thinning over time, shaped by the sun's own cycles of activity and by the shifting pressure of the interstellar medium pushing back against it from outside. Two crossings, 6 years apart, produced two meaningfully different boundary structures, and only Voyager 2's fully functioning instruments made it possible to know that for certain, rather than simply assuming both crossings must have looked roughly the same. There was one more finding buried in Voyager 2's data, subtler than the others, but in some ways just as significant for how scientists now think about our place in the galaxy. Once Voyager 2 was confirmed to be traveling through interstellar space, its still-functioning plasma instrument allowed scientists to directly measure the density and temperature of the plasma immediately outside the heliosphere for the first time in human history. What they found was plasma noticeably warmer and denser than most existing models had predicted, hinting that the interstellar medium immediately surrounding our solar system is not the simple, uniform, empty void many scientists had long assumed it to be. but a more complex, structured environment, possibly still bearing traces of compression from the heliosphere, pushing outward against it from within, or shaped by unrelated interstellar structures, slowly drifting through that region of the galaxy over vast stretches of time. Every future mission designed to study the outer boundary of the solar system, every model built to predict how the heliosphere shields Earth and the rest of the solar system from harmful cosmic radiation, now rests in part on that single set of direct measurements, gathered by an instrument that, on its identical sister spacecraft, had gone permanently silent decades earlier. So, when people ask what Voyager 2 actually did that Voyager 1 never could, the honest answer is not one single achievement, but an entire chain of them, each one depending on the last. It is the only spacecraft ever to have visited Uranus and Neptune, giving humanity its only close-up data on an entire class of planet that may be the single most common type of world found throughout the galaxy. It gave us our only direct glimpse of active plumes erupting from a captured Kuiper Belt world, decades before any mission was ever designed to study one deliberately. And when it finally crossed into interstellar space, it did so carrying the one instrument capable of measuring that historic crossing directly, catching a boundary far more porous, dynamic, and structurally complex than any existing model had predicted, and revealing an interstellar environment just beyond our solar system that is stranger, denser, and far more textured than scientists had ever expected to find waiting for us out there. Both spacecraft are still out there right now, drifting further from home with every passing second, their faint radio signals taking more than 20 hours to reach Earth, even traveling at the speed of light, their plutonium power sources fading a little more with each passing year as engineers back on Earth shut down instrument after instrument one by one to stretch out whatever tiny amount of power still remains on board. Sometime in the next few years, the last working instruments on both Voyagers will very likely go dark for good, and humanity's direct physical presence at the true edge of the solar system will end, at least for a generation or more, until some future mission is designed, funded, built, and launched to follow in their path. When that day finally comes, Voyager 1 will be remembered, correctly, as the spacecraft that got there first, the one that claimed the historic milestone in the front page headlines. But it will be Voyager 2's data, gathered from worlds no other spacecraft has ever touched and from a boundary no other functioning instrument has ever crossed while still transmitting home, that scientists will still be quietly unpacking for decades to come. Because it did not merely confirm what humanity thought it already understood about the edge of our solar system, it proved that the edge of everything we call home is far stranger, far more dynamic, and far less understood than anyone dared imagine, before that quieter, slower spacecraft finally got there and refused to stop sending data back. There is something almost poetic in the fact that it was the slower spacecraft, the one that took the longer road, that ended up teaching us the most. Voyager 1 sprinted ahead and claimed the finish line first, and history will always remember it that way. But Voyager 2 took the scenic route through the outer solar system, stopping at worlds its twin would never see, carrying instruments its twin would eventually lose. And in doing so, it became something more than a fast follower playing catch-up decades later. It became the only complete record humanity has ever gathered of an entire class of planet, the only witness to an active eruption on a captured world from the icy edges of our solar system, and the only working set of eyes ever to watch, in real time, as our solar system finally gave way to the galaxy beyond it. Somewhere out past the reach of sunlight, past the last faint traces of the solar wind, Voyager 2 is still out there, still calling home across billions of miles of empty space, carrying with it the last direct measurements humanity may have of that boundary for a very long time. And every model, every textbook, every future mission built to understand where our solar system truly ends will trace its foundation back to those final, unrepeatable years when one aging, unglamorous spacecraft quietly did what no other machine, before or since, has ever managed to do.